Hello. Today we are going to study Chapter 3 about project management. First, we would like to define what is a project. A project is a single unit, have a beginning and an end, have different activities and different time and cost for each activities. In general, you can have a project, for instance, building a construction building. That's a project that maybe takes 2 years and have several activities, or a research project, or developing a new product or service. In general, the management of projects involves 3 steps or 3 phases: planning, scheduling, and controlling. In the planning, you setting the goals and define the project, organize your team. In scheduling, you relate people, money, and supplies to activities. And in controlling, you monitor resources, costs, quality, and budgets to see if your plan is working properly. For instance, in order to plan the project, you have several activities to develop, also for scheduling the project and for controlling the project. In the planning the project, there are several tools that you have available, like time and cost estimates, budgets, engineering diagrams, cash flow charts, material availability details. In scheduling the project, you have certain tools. We are going to study in this chapter CPN and PAIR, 2 network techniques in order to schedule the project. Also, maybe you have heard about Gantt charts, another type of charts like milestone charts and cash flow schedules. For controlling the project, you control the project with budgets, with a report of delayed activities, and a slack activities report. A slack means that the activity has some days or weeks of a slack, and it can be delayed without delaying the whole project. In project planning, you have to establish the objectives, define the project, define the structure of the project and the resources that you need, and then form the organization. There are many techniques for doing that. In the direction of project schedule, show the relationship of each activity to others in the project. Identify the precedence relationship among activities, that's very important, and the times and cost estimates for each activity. There are certain project management techniques, among them Gantt charts, the critical path methods, and the program evaluation and review technique PERT. As a Gantt chart, maybe you are familiar with this. You have several activities and different months or times. Then you have different activities like design, prototype, test, revise, production. Then the length of the bars that you see in a Gantt chart is the duration of the activities, and some activities cannot begin until the previous activity has been completed. For instance, in the case of a Delta jet, when the plane arrives to an airport, you have to deplane, the passenger have to leave the plane, then you have to fuel the plane, because the plane is going to leave maybe in half an hour to other destination. The engine injection water, you have to offload the container, the cargo, then to service the main cabin door, the lavatory servicing, the drinking water, cleaning the cabin in first class and economy sections. Then you have to load all the new luggage for the new passengers, receive the passengers, loading the baggage, and then boarding the passengers. And then there are several, the duration of these activities, in this case minutes, can be for several minutes to longer, and some activities cannot start until the other activities have been completed. Now, project controlling is a close monitoring of resources, cost, and quality. You would like to control if the product that you design is behaving, the plan that you had, as was supposed to to perform. For instance, if you are building a construction and you are 1 week or 1 month delay, then you would like to shift resources and maybe assign new crews and people to certain areas that are delayed. But in order for you to know that they are delayed, you compare the planned situation to recurring situation and you look for deviations, and then there are several tools in order for doing that. Now, per CPM, we are going to study was developed in the 1950s, CPM by DuPont in 1957, and PER by Booz Allen and Hamilton of the US Navy for Polaris missile in 1958. It's a network technique, we are going to explain why. Consider the precedence relationship and the interdependence. Each uses a different estimate of activity times. There are 6 steps to define the project and prepare the work breakdown structure, develop the relationship among the activities, draw the network connecting all the activities, assign time or cost estimates to each activity, compute the longest time path through the network. This is called the critical path. And use the network to help plan, schedule, monitor, and control the project. You can answer some questions like this when you develop a per CPM. When will the entire project be completed? What are the critical activities or tasks in the project? Which are the non-critical activities? What is the probability that the project will be completed per a specific date? Is the project on schedule, behind the schedule, or ahead the schedule? Is the money spent equal to, less than, or greater than the budget? Are there enough resources available to finish the project on time? If the project must be finished in a shorter time, what is the way to accomplish this at the least cost? We are going to study all of this in this chapter. Now, before that, I told you that per CPM is a network technique. In a network, you identify the activities in a project either in nodes or in arrows. We are going to use in this course activities on nodes. For instance, in this case, activity C comes before after activity B has been completed, and activity B after activity A has been completed. In this other case, in B, you can see that activity C here is going to start after activities A and B are completed. In this case, B and C cannot begin until A is completed, in the case number C. In other cases here, in case D, C and D cannot begin until both A and B are completed. In this other case, C cannot begin until A and B are completed, and D cannot begin until B is completed. In this case, B and C cannot begin until A is completed. As you can see, B and C one after A, and D cannot begin until both B and C are completed. Let's study or understand this method with an example. Milwaukee Paper. Milwaukee Paper Manufacturing had long delayed the expense of installing advanced computerized air pollution control equipment in its facility. This is a project. The project is installing an advanced computerized air pollution control equipment. When the board of directors adopted a new proactive policy on sustainability, it did not just authorize the budget for the state-of-the-art equipment. It directed the plant manager, Julianne Williams, to complete the installation in time for a major announcement of the policy on Earth Day, exactly 16 weeks away. Under a strict deadline from her bosses, Williams needs to be sure that installation of the filtering system progresses smoothly and on time. Given the following information, develop a table showing activity precedence relationship. Then, there are several activities to be completed in this project. Activity A, build internal component. This activity doesn't have immediate predecessors. Activity B, modify the roof and the floor. Also, this activity B doesn't have immediate predecessor. Activity C, construct collection stack. You have to start after activity A has been completed. Activity D, pour concrete and install frame. start after A and B has been completed. Build high temperature burner after activity C has been completed. Install pollution control system, activity C is completed. Install air pollution device cannot start until activities D and E are completed. And inspect and test until activity F and G has been completed. Then, if we draw a network for Milwaukee paper, this is the presence relationship. The same that we saw here in this table, here, you can review step by step here. Activity A and B, they don't have presence relationship. Then you start with activity A and B, but after that, activity C start after A, and activity is D after A and B has been completed. Then activity E after C, activity G after E and D has been completed, activity F after C, and activity H after F and G has been completed. Now, in order to perform a critical path analysis, we need more information. Remember, the critical path is the longest path through the network, and is also the shortest time in which the project can be completed. Any delay in critical path delays the whole project. The critical path, they have no slack time. If you delay by only 1 minute that activity, the whole project is going to be delayed. Let's assume in the case of Milwaukee paper that we have some estimates about the time required for each activity that are going to be shown in the table in the next slide. In this table, you can see that each activity has a certain number of weeks to be completed. Of course, if you do these activities in sequence, it will take 25 weeks to complete. But as you know, some activities can be done in parallel, and some activities cannot start until other activities has been completed. Then we need to draw the network first, and then using this time, we are going to determine the critical path. For doing that, we define 4 times. The earliest start is the earliest time in which an activity can start. The earliest finish, earliest time in which an activity can be finished. The latest start, the latest time in which an activity can start, so as not to delay the completion time of the entire project. And the latest finish, the latest time at which an activity has to be finished. Then we are going to establish this symbol or this format. We are going to name the activities here in the center, activity A for instance, and here the duration of the activity. 2 is 2 weeks, the duration of the activity. The early finish is going to be here, the earliest start here, the latest start is going to be below the earliest start, the latest finish below the early finish. Then we do what is called the forward pass. You can read this more in detail in the presentation, but to explain this video, I am going to go directly to the case of Milwaukee paper. We start at time 0. The earliest start, the early finish is always the earliest start plus the activity time. The activity time of the start is 0. Then we start with 0. Now activity A has a duration of 2. Can begin at time 0 because it doesn't have any presence relationship, and you have 0 plus 2, then the early finish is going to be 2. Activity B also can start in 0 because it doesn't have presence relationship, plus 3 is going to be the early finish is going to be 3. Activity C comes after A. Now the earliest finish of activity A is 2, is going to be the earliest start of activity C, 2. C cannot start before time 2. And activity C has the duration of 2 weeks, then 2 plus 2 equal to 4. Then we go to activity D. Activity D is here. In this case, we have something interesting. Activity D comes after A and B. Now B finish at time 3 and A finish at time 2. Since D needs A and B, then you would like to choose the maximum between 2 and 3, which is 3. It's going to be the earliest start of activity D. And the activity D duration is 4, then you have 7. Then the rest of the network, activity E start, since this is finished at 4, and then start at 4, plus 4 is 8. Activity F is goes after activity C. Then the early finish here is 4, the early start here is 4, plus 3 is 7. Activity G is after E and D. The E is the maximum between A and 7, which is 8, plus the duration of G, which is 5, is going to be 13. And then activity H is the maximum between 7 and 13, which is 13, plus 2 is 15. Then we know that the duration of the project is going to be 15 weeks. Then we do the backward pass. This is the forward pass. The backward pass, we start then from the last. We repeat the latest finish is equal to the early finish. This is something that we assume. Then we, instead of adding, we subtract 15 minus 2 is going to be 13. Then the latest start is the latest finish minus the activity time. Then if we do that, for instance, in this case, the latest start was 13 is going to be the latest finish in activity if, that is before 13 minus 3 equal to 10. And then we continue for doing that. However, here we have a special case. Look, activity C, or after activity C, comes activity F and E. The earliest, the latest start of activity F is 10 and activity E is 4. Then instead of having the maximum, when you do the backward pass, you select the minimum between 4 and 10, which is 4, and 4 minus 2 is 2. And then we complete the rest of the network. Now, the activities in the critical path has, for instance, here you have the early finish is 2 and the latest finish is 2. 2 minus 2 is 0. It is saying that the earliest start and the early finish, 0 minus 0 is 0. Then you do subtraction vertically. For instance, here the slack is 0, here is 0. Here instead you have 13 and 7, which is 13 minus 7 is 6, which is the same than 10 minus 4 is 6. Then here you have a slack of 6 weeks. Here in this activity you have, for instance, 8 minus 7 is 1, which is the same as 4 minus 3, and slack of 1. Then you select the activities who has a slack of 0. Those are the activities in the critical path. In this case, the activities for the critical path have 0 slack are activities A, C, F, G, and H. Then the non-critical activities are F, D, and B, because they have a slack. In this case, the slack is 4 minus 3, 1, A minus 7, 1. In this 30 minus 7 is 6, which is mean that activity F can be delayed by 6 weeks, and the whole project still is going to be 15 weeks. Then we know that activities A, C, E, G, and H are the critical activities, that the duration of the project is 15 weeks, and then I have to watch closely and control closely those critical activities, because if they delay by 1 day or 1 minute, they are going to delay the project. Instead of 15 weeks, it's going to be 16 or 17. Remember, we have 16 weeks is the goal to complete this project. With the data that we have, we can complete it in 15, 1 day before. This is the critical path. The project expected completion is 15 weeks. There are 5 activities on the critical path, and 3 activities are no critical path and have a slack time. Then that's the critical path method. Now, sometimes you develop a project and you would like to finish the project before the time that was expected. That's called crashing a project. For instance, it's not uncommon to face the following situation: the project is behind schedule, or the completion time has been moved forward. Then shortening the duration of the project is called project crashing. You have to take several things into account to consider when crashing a project. The amount by which an activity is crashed is in fact permissible. Taking together the shortened activity durations will enable us to finish the project by the due date, the new due date. The total cost of crashing is as small as possible. We would like to minimize the cost, because if we would like, instead of 15 weeks, we are going to see that, to complete the project in 14 or 13 weeks, we need more people, more resources, then the cost of the project is going to increase. But we would like that increase to be as small as possible. The step in project caching, the first is calculating what is called the crash cost per period, which is the crash cost minus the normal cost divided to the normal time minus the crash time. Now, we are giving this information. Normally, we are giving this information by operations, accountants, financial department, or project managers that control the time and the cost. Using the activities, find the critical paths, identify the critical activities. Then, the first step is to select just the critical activities. We are going to crash the project just for the critical activities. Is there only one critical path? Select the activity with the critical path that can still be crashed and has the small crash cost per period. If there is more than one critical path, select one activity for each critical path so that each selected activity can still be crashed and the total crash of the selected activity is the smallest. We are going to see this case. If we already arrive at the new due date, then we finish. If not, we continue to crash the project. Suppose the plant manager at Milwaukee Paper Manufacturers has now given only 13 weeks instead of 16 weeks to install the new pollution control equipment. As you recall, the length of Julianne Williams' critical path was 15 weeks. We already calculated the critical path, but she must now complete the project in 13 weeks. The company's normal and crash times and normal and crash costs are given in this table. Then we apply these formulas to calculate the crash cost per week, and we identify which activities are in the critical path. Remember, the activities in the critical path, the original critical path was A, C, E, G, and H. There are 3 non-critical activities. We calculate the crash cost per week. Remember, is divided, we subtract the crash cost minus the normal cost is 22,750 minus 22,000 is going to be 750 divided into the normal time minus the crash time. This means that normally we can we complete this activity in 2 weeks, but it is feasible to complete this activity in 1 week. Of course, we need more people, more resources, more equipment, and that's the reason that the crash cost is higher than the normal cost. And in this case, 22,750 minus 22,750 divided into 2 minus 1 is 750. In this other case, 34,000 minus 30,000 is 4,000, and the normal time minus the crash time is 3 minus 1 is 2. Then 4,000 divided into 2 is going to be 2,000. Then you calculate the crash cost per week. You can review this calculation in this table. And for the critical activities, which are 5, we select the one with the least crash cost per week, which is activity A with 750. Then we are going to crash activity A. We can only crash 1 week. Remember, we need 2 weeks because originally we had 15 weeks. We have to go to 13 weeks. Activity A can only be crashed by 1 week. Then we have to do this in 2 steps. This is the calculation of the crash cost per week. You can review this calculation. Then this is the original critical path method, if you remember. Then crashing the original activity A has 2. In the new critical path, activity A has the duration of 1. We recalculate the critical path. Now the duration of the project is going to be 14 weeks. Still, we need to crash another week. And there is now, look at this, 2 critical paths, A, C, E, G, and H. And down here you have B, D, G, and H, because this activity, you subtract the right side of the left side, 12 minus 12 is 0, 7 minus 7 is 0, there is no slack. Here there is no slack, also here there is no slack. Then when there are 2 critical paths, the method says for the critical activity, select the one with the least crash cost. In this case, in this first one, you can verify that it's activity C with 1,000, and in the second one is the activity D with 1000 also. Then 1000 plus 1000 is going to be 2000 because you have to add the two critical paths. However, there is one activity here, activity G. Activity G is common to both of the critical paths. Then, and the activity G, crashing the activity G is just 1500. And 1500 is less than 12,000, and it's an activity that is common to both critical paths. Then in this case, there is an activity that is common to both critical paths, and the crash cost per week, which is 1500, as you can see here in activity G is 1500. Then we can now crash another activity, in this case activity G for 1 week, only 1 week. Then the new activity G is going to be 4 weeks, as you can see. Activity A stays in 1 week, and this is the new critical path. And now we have 13 weeks. We have still 2 critical paths. The total crash cost is the original 750 for activity A, and the 1500 for activity G, which is 2250. This is the total crash cost and the duration of the project, and there are 2 critical paths in the project. This is called crashing a project. You can read the advantage and disadvantage of per CPM, sometimes and limitations. You can read this in the presentation. But with this, we calculate. We are here. You have an example. You can review. You have the answers here in the bottom. Read the questions and try to write to these answers. But this is part of the presentation that you have in Canvas for this week number 3. With this, we finalize this video, and thank you very much.